Okay, so the second piece is just a bit more complicated, and it's working with negative z-scores. So you got to kind of like flip the table around to work through this. I'll just talk about it a little bit, and I've just separated it out from the general topic of percentiles from the first video. So just to recall, we had two scores: the math score and the English score, from the two standardized tests for the math test and the English test. Both scores of 76, mean of 70, and as we saw, the key difference was the standard deviations. For the math test, it was 3. For the English test, it was 12. Converted both of those to z-scores, right? The standard normal curve, mean of 0, standard deviation of 1. That is by definition. I always know that's true. I don't even have to do it. I don't have to do that calculation for every score in the distribution. The z-score for the math test is 2.0, and the z-score for the English test is 0.5. Okay, so as I said before, for the z-score, the person is 2 standard deviation units above the mean, up in the upper tail, which puts them, the performance as being relatively exceptional. And for the English test, really with a standard deviation of 12 and a score of 76, that difference of 6 is half a standard deviation unit. A standard deviation unit being 12 for the English test. So above average, but not super exceptional. Okay, and we know that from the table where we look up the values, and the body of the table gives us the proportion of scores that are between the mean of 0 and a given z-score. We looked it up for the math test, right? So it's a positive z-score of 2. So 0.4772 of the scores are between the mean of 0 and the z-score of 2. I take that 0.4772, add it to the 0.5, and the percentile rank for the student on the math test is 97.72%. Of the other students who completed that test scored below 76. Did the same thing for the math test, or the English test, I mean. 0.5, z-score of 0.5, half a standard deviation unit above the mean. And the number of scores that reside between the 0 and the 0.5 is 0.1915. So 19.15% of the total scores are between the mean of 0 and the z-score of 0.5. Add that to the 0.5. And the reason I add the 0.5 because the 0.5, half the scores are always below the mean, because for any normal curve, the mean, median, and mode are the same value. So 0.5 plus 0.1915 means that the percentile rank for the child on the English test was 69.15% of the students scored below 76 on the English test. So performance is not quite as, relative to the peers, the child's peers, scores on the English test are not quite as good as the child's score on the math test. Child's on the math test was quite exceptional. On the English test, the child was above average, but nothing super exceptional. Okay, and we saw how to use the columns, right? So z-scores to the first decimal place are in the first column, and then the remaining columns over carry out the z-scores to the second decimal place. All right, so for a z-score of 0.36, that's 0.3 and carry over to the 6 to the second decimal place. So 0.36 is right here. Okay, negative scores. The standard normal curve is symmetric about the mean. So the shape of the curve on the left side is the same as the shape of the curve on the right side. So it's a mirror across the if I folded the distribution in half along the axis for the mean, if I fold the distribution here, this line here will parallel and overlap this line here. So a z-score of a positive z-score, if I look at that same score on the negative side, the area under the curve is the same, but it's below the mean. So now, let's say I have a z-score of not 0.36, but of negative 0.36. If I have a negative, I'll always have a negative z-score for scores that are below the mean. So now I know that half the scores are below the mean, and now I'm going to get this piece right here. What proportion of scores are below the mean of 0 and the negative z-score? So for a z-score of negative 0.36, the area under the curve is 0.1406. That's this area here. But for the percentile, I need to subtract that area from the 0.5 to get this area in the curve right here. So the tail end of the curve is what the percentile rank will be. So I take 0.50 minus 0.1406, which is 0.3594. Okay, now what I would like you to do is attempt to figure out the percentile for the 4 sets of scores here. For all 4 scores, the mean is 100 and the standard deviation is 10. I want you to calculate the percentile for a score of 109.4, 111.6, 91.8, and 76.2. And the answers, you can pause the video and answer the questions, and you'll see the answers on the following slide after you've restarted this video. Okay, if you've attempted the questions, for the first one you should have got a percentile of 82.64. For the second one, a percentile of 87.70. For the third one, a percentile rank of 20.61. And for the third one, a percentile rank of less than 1%, or 0.87%. You'll see that you have to calculate the area under the curve. You're going to get the z-scores first. And then for the first two, you add the area under the curve from the table, 2.5. And then for the second two, because they are negative z-scores, you take the value from the table and you subtract it from 0.5. So walk through it, and if you didn't get it right, just check your answers and check them in the table.